Hello everyone. Today we are going to talk about contrast media. Essentially, why is contrast media even important? First of all, before talking about contrast media, let's talk about the first word, contrast. So what is contrast? Simply put, contrast is nothing but an obvious difference present between two or more things. As depicted in the image on screen, we can see a sphere, and towards the left half of the image, the background is dark, and towards the right half of the image, the background is bright. So, in which half of the image, left or right, do you think it is much more easy to delineate the border of the sphere? Well, obviously, it is towards the right half. And why is that? It is due to the obvious difference present between the two or more things, that is, the background and the sphere in this image. There is a contrast. So, that is the reason contrast is necessary because the difference in density among various tissues in the body usually are too small to provide adequate contrast for visualization of anatomical details. So we have to compensate for this. So essentially, we have to increase the density or decrease the density. Why? To make a contrast, we have to increase the density. That is, we have to brighten the object or decrease the density. That is to make the target much more radiolucent. So simply based on this, we can divide contrast media into two, that is positive or negative. If the contrast agent increases the net density of the target, that is, it makes the target much more radio opaque, then it is radio opaque or positive contrast agent. If the contrast agent makes the target much more negative, that is much more black, therefore it is also called as radiolucent or negative contrast agent. Let's talk about negative contrast agents first and the mechanism. Radiolucent contrast media. Basically, the absorption of X-rays by a substance is depend upon several factors, and one of them, one of the important one, is the atomic weight of the substance. Radiolucent contrast media are materials with low molecular weight. Since they have low molecular weight, they will cause less attenuation of the radiation. That is, they stop less amount of radiation. Therefore, much more radiation or rays pass through the object. Therefore, much more rays will reach the image receptor. That is nothing but there is greater density on the image receptor. Therefore, the object or the target appears much more black. That is much more radiolucent. This characteristic is very useful when our main objective is to demonstrate an anatomic structure against the dark background. Obviously, to provide us a. And examples of this radiolucent or negative contrast agents are air, oxygen, carbon dioxide, and nitrous oxide, which are materials essentially with low molecular weight. In fact, most of the available gases have been used at some point as negative contrast agent with varying amount of results. However, these four gases, that is the air, oxygen, carbon dioxide, and nitrous oxide, are most commonly used negative contrast agents. The negative contrast agents can also be used in conjunction with positive contrast agents, as done in barium procedures. Like if we do it for swallow, double contrast barium swallow. Or we can, if we use both of them, the positive and a negative contrast, for enema, it is called as double contrast barium enema. The first two compounds, that is the air and oxygen, can be dangerous during certain procedures because these are the gases which have potential to form emboli. But the next two, the last two, the carbon dioxide and the nitrogen, do not pose the risk of formation of gas emboli, and therefore these can be used much more safely. They are also able to be absorbed rapidly by the body. Therefore, this factor can be advantageous when rapid absorption is desired. Now let's talk about positive contrast agents, that is the radiopaque contrast agents. Because of their high atomic numbers, positive contrast agents cause an increase in the attenuation of X-ray. They have high molecular weight, they also have high atomic numbers. Because of that, it will cause much more attenuation of the radiation, meaning that much less rays pass through the target itself, meaning that much less receptors are activated, much less density of them are activated. So the target, the object itself will appear bright, that it appears much more radio opaque, therefore increasing the contrast. Let's stop our talk on contrast media here for a second. If we're talking about contrast media, let's talk about the term osmolality, which is very commonly used in terms of contrast media. So what is osmolality? Osmolality is the number of solute particles in 1 kg of solvent. We all know osmolarity of plasma around 3 is around 300 milliosmoles per kg. Well, let's take a hypothetical example. Here we have a blue box which has an osmolarity of 300, meaning that there are 300 particles in that box right now. There is another box, the orange one on the right, which has double the osmolarity of the blue one, that is 600. Now, if there is some sort of communication between the two, where do you think the particles will move, from left to right or right to left, from blue to orange or orange to blue? Obviously, as we all know, there is movement of particles from higher concentration towards the lower concentration. So in this case, there is obvious movement of solutes from orange box, which has osmolarity of 600, to the blue box, which has osmolarity of 300. Now, the resultant of this movement can be good or bad, depending on what it is. If we use the same logic for plasma and contrast media, the blue box depicting plasma, which has osmolarity of 300 milliosmoles per kg, and if the orange box depicts the contrast media. So if we use a contrast media which has higher osmolality when compared to plasma, there is movement of particles from contrast media into the plasma, into the cells much more. Now, this movement is obviously essential for it to produce radio opacity, but the problem with this is that if the particle which is moving from a contrast media to our vessels, if it is toxic, it will lead to much more complication. So certain group of contrast me agents produce side effects, more side effects. Certain group produce much less side effects. So why is that? Let's find out it in next slides. Uh, Positive contrast media can be divided based on whether it is having iodine or not. Iodinate into iodinated and non-iodinated contrast. Well, historically, if you talk about brief history, interestingly, air was the first recognized contrast agent which was used in radiographic examination of chest. Soon, bismuth salts were used as for contrast agent in upper GI studies of cat, but obviously it was toxic, so it was stopped and it was replaced with barium sulfate. Interestingly, in early 1920s, syphilis was treated with a high dose of sodium iodide. And interestingly, during radiographic examination, it was found that sodium iodide was radio opaque, owing to its iodine content. Soon, the first iodine-based contrast agent was used. Essentially, it was nothing but a pyridine ring, which is benzene, to which a single iodine atom was added. Everything was great. So, what was the problem? The problem with this was that the iodine atom was single, therefore the radio opacification produced was less, and the compound was toxic, and it produced much more, varying degrees of adverse reactions. So soon there was a hunt for the ideal contrast medium. What makes a contrast media ideal? It should obviously be easy to administer, it should be non-toxic, it should be a very stable compound, and it should not dissociate it when injected into the body. And it should obviously, after the work is over, it should be rapidly eliminated whenever necessary. It should not be carcinogenic. Obviously, it should be cheap as well. It should not be much viscous, and it should easily be tolerated by the patient. So based on this, uh, benzene ring was taken, and as we all know, there are six hydrogen atoms around the benzene at six positions. So at 246 position, the hydrogen atoms were removed, and iodine was introduced, obviously to produce radio opacity, to produce contrast. But the problem with this compound, as depicted on the image, was that it is not water soluble. Since it is not water soluble, it cannot be safely administered intravenously. So therefore, we had to make it water soluble somehow. So at position number one, hydrogen was removed and carboxyl group was added. COOH was added. All was great. Now this was water soluble. It can be injected intravenously. But the problem with this compound was that because of the hydrogen atoms at the position 3 and 5, it was still toxic. So we had to replace those hydrogen atoms with compounds R1 and R2, which in most of the cases are nothing but compounds with combination of sodium and meglumine, which is nothing but an methyl glucamate. Before all this, first of all, why did we only use iodine atom to replace hydrogen? Why did we use only iodine as contrast media? Because iodine is a stable compound and it carries to the organ under examination much easily. And the carrier molecule in these contrast media are also organic, which are mainly made of carbon. And these are obviously low toxic and they're highly stable as well. And iodine is used because it is relatively safe, and the K edge of the iodine, it is approximately 33 keV, and this keV is much more close to the mean energy of the X-rays we use in diagnostic radiation. Therefore, it produces much better radio opacification. So we divided the contrast agents, positive contrast agents, into ionic and non-ionic broadly. So what does this mean, ionic and non-ionic? Well, simply put, if we take a compound, inject it intravenously, if it dissociates and it forms ions, that is cations and anions, that is it forms two particles, a cation and anion, then it is called as ionic. If it doesn't dissociate, or it doesn't form any product, or if it forms a product, it is not an ion, it is a neutral compound, then it becomes non-ionic. How is this important? Well, it is important because if we give a contrast agent and it dissociates and it forms ions. Ions is nothing but electrically charged substance. Now, these substances can um, go into our body tissues like the myocardium and brain cells, and they can interfere. Since it is an ion, it can interfere with the electrical activity in the heart and the brain. It can cause arrhythmia, it can cause seizures. That's the problem with any ionic B compounds. Now, as depicted on the screen, what does this ionic monomer mean? Well, simply put, we can see on the diagram that the compound gives three iodine atoms, that is from the position 246, which is great. So, three iodine atoms are responsible for radio opacity from this compound. But additionally, to produce these three iodine atoms for radio opacity, this ionic monomer, remember it is an ion. It is monomer because it has a single benzene ring. That is the reason we call it monomer. But since it is an ion, when we give it inside the body, it dissociates into positive cation and negative anion. That is two particles. Any ion forms two particles. So what does it mean? In order to get three iodine from the compound, it also will give us two particles, positive and negative. This is called as the effect ratio, which is nothing but the ratio present between the number of um, iodine atoms given from from the compound and number of particles from the compound, which is 3 is to 2 in this. That is three atoms and two particles. Now, this is definitely problematic because the effect ratio for ionic monomer is 3 to 2. That is the number of particles for every three iodine atom is 2. Therefore, the number of particles we are getting are very high. Therefore, it increases the osmolality of the contrast media, that it is highly hypertonic. As we already discussed in previous slides, that since the osmolality is more, the contrast media crosses the cells more, it enters the cells more, and since it is ionic, it interferes with the electrical activity of the cell, and it is also hypertonic, which and the osmolarity of ionic monomers is very high in the rate of 1200 to 1500, in some cases 2000 milliosmoles per kg. Therefore, it has obviously high amount of side effects. So it was acknowledged and agreed that somehow we have to increase the effect ratio. So how do we do it? One way is found out that if we take two ionic monomers and join them at the level of R2, we can create an ionic dimer as depicted in this image. The advantage of this is that this ionic dimer, it still gives us six iodine atoms, but the advantage of is that it is still a single compound. That is, if we inject IV into the human body, it dissociates obviously because it is an ion. It is an ionic dimer. It dissociates into two particles, that is a cation and anion. But remember, the amount of iodine is given is double that of ionic monomer. That is, ionic dimer is giving us six iodine atoms. So the effect ratio will be 6 is to 2, two particles cation and anion, which is 3 is to 1. So, which is actually double that of the ionic monomer. And resultantly, there is also a decrease in the osmolality. The osmolality of ionic monomers was in the tune of 1200 to 1500 milliosmoles per kg. But in case of ionic dimer, the osmolarity is half. It is around 600 milliosmoles per kg. And even the effect ratio is 6 is to 2, that is 3 is to 1, which reduce the side effects as well when compared to that of ionic uh, and be it ionic monomer or ionic dimer, it has a carboxyl group. And later it was found out that the carboxyl group present in ionic contrast agents is responsible for neurotoxicity. And not only that, we know that the side effects, the adverse effects in ionic compounds is mainly due to their ability to form ions and disturb the electrical activity in the cells. So what if there are no ions at all? What if a compound is there which will form neutral particles after dissociation? Therefore, it will not react with tissue at all. Gradually, non-ionic compounds were formed, invented. These are low osmolar agents and they do not dissociate into two particles into solution, making them much more tolerable and much more safer when compared to ionic contrast agents. So, non-ionic compounds were discovered, invented. Non-ionic compounds based upon the ring, it can be a monomer or dimer. Now, the main difference with them is that the side chains, the R1, R2 chains, which in which for ionic compounds we use sodium and meglumine compounds, here it is completely replaced with hydroxyl compounds. Uh, the main advantage that arising through the change in chemical structure in non-ionic compounds are that the first is that obviously we know the negatively charged carboxyl group is eliminated, thereby reducing the neurotoxicity. And the second is that the elimination of the positive ion reduces the osmolality. There is no formation of particles, two particles like ionic, therefore reduces the osmolality. So even the monomer in case of non-ionic compound has an osmolality of around 600 milliosmoles per kg, and it is much more tolerable. In fact, non-ionic monomers can actually be used for intrathecal and vascular. And if we talk about the effect ratio of non-ionic compounds, in this case, non-ionic monomers, uh, as clearly depicted in the image, the numerator of the effect ratio is 3 in this case, because of three iodine atoms at position 2, 4, and 6. But the denominator, the particle is still 1. It doesn't dissociate. Even if it dissociates, it produces a neutral compound. Therefore, it has an effect ratio of 3 is to 1, making it much more tolerable as well. Now, all in all, it was good. Non-ionic monomers has good effect ratio of 3 is to 1. It doesn't dissociate into any particles. The only issue with, not an issue, but only problem with it was that it has an osmolality of 600, which is, when compared to that of plasma, it is double. So what if we reduce the osmolality? What if we can form a compound which is isoosmolar to blood plasma? Well, taking from non-ionic monomers from the position 2, 3, and 5, 6, the compounds were joined to form non-ionic dimers. That is, it has two rings. As depicted in this image, the non-ionic dimer still has, it gives 6 iodine compounds. That is, the numerator of the effect ratio is 6, and the denominator still stays the same because it doesn't lead to production of any compound post-dissociation. That is, the effect ratio is 6 is to 1. And because of this, which is actually double that of the non-ionic monomer as well. An important feature of these is that they are completely isotonic. Their isoosmolality combined with slower diffusion. Why slower diffusion? Because their osmolality is similar to that of plasma. And then because owing to their larger molecules present in them, there is much less movement of contrast agents into the cell, therefore leading to much less adverse effects when compared to that of previous compounds. So these molecules essentially represent a gold standard water-soluble iodine-based contrast medium. Well, we have talked a lot about post-contrast media, especially positive and iodinated contrast media. Now it can be confusing as well. So in order to summarize it quickly in a single image, I've created an image and posted it on my Telegram channel as well. Broadly, we can divide positive contrast media into ionic and non-ionic as depicted. And subsequently, ionic and non-ionic can be divided into ionic monomers and ionic dimers. Ionic monomers, uh, well, they're self-explanatory. Ionic compounds Since they are ionic, they produce two compounds, that is a cation positively charged and anion negatively charged. Non-ionic do not produce any compound, that is, it is neutral. Now, monomer, regardless of whether being ionic or non-ionic, it is a monomer. Therefore, it will have a single ring. Therefore, it will give us three iodine atoms. A dimer will it has two rings. It will give us six iodine atoms. Now, in ionic, it is attached with the carboxyl group COOH. Non-ionic, it is attached with hydroxyl group. Now, the iodine depends whether it is monomer or dimer. Three iodines for monomer to six iodines for dimer. Now, particle ratio, it depends whether it is ionic or non-ionic. Ionic will give us two particles, non-ionic will give us single particle. Based on this, we can calculate the effect ratio. Obviously, the higher the ratio, the better it is for us. The much lesser side effects is for us. Obviously, the osmolality, the ionic compounds, since it produce two particles, therefore osmolality will be much more. Therefore, ionic monomers also called as HOCM, high osmolar contrast media, the ionic dimers, as well as non-ionic monomers with osmolarity of around 600 to 800. They are also called as low osmolar contrast media. Low when compared to ionic monomers, not obviously when compared to plasma. It is still high when compared to the double plasma, but when compared to ionic monomers, HOCM, it is much less. In fact, it is half or less than that. Now, the gold standard non-ionic dimers, which has a high effect ratio of 6 is to 1, which is actually isoosmolar. It's called as IOCM, which is isoosmolar contrast media. Um, yeah, now coming to examples, ionic monomers such as EM, the examples include urographin, gastrographin, ditrizoate, and the ionic dimers, which is commonly used as well, ioxaglate, and non-ionic monomers, which is very commonly used in India, the iohexol, homipac, the iopamidol, and iomiprol. Now, the gold standard non-ionic dimer example, the IOCM is iodixinol, which was previously not available in India, but right now even iodixinol is available in India, obviously. And in cost wise, ionic are much more cheaper, non ionic are much more expensive. The disparity between them is reduced when compared to the past, but still, non ionic is much more expensive. So it is much less used. Non ionic dimers, especially, is much less used in India. So based on all the data we have, based on all these countries' consideration, we have to decide what contrast will be much suitable for the patient. If there is history of anaphylactic reaction or anaphylactoid reaction to the contrast media, it is much more better to use non-ionic compounds when compared to ionic compounds. Obviously, it's much if it is available, non-ionic dimers like iodine is much more better. But if there is in history, it is much better to use non-ionic compounds. But it obviously doesn't mean that non-ionic dimers like iodine is completely safe from adverse reactions. Obviously, there are certain idiosyncratic reactions which can occur with non-ionic dimers as well. Now, complications associated with contrast media, I didn't cover it in order to keep the lecture short in this video. If needed, I'll cover it in some other video. And also, I didn't include barium contrast nor the MR specific contrast agents or ultrasound specific contrast agents in this video in order to make it short. If needed, I'll make a separate video for that. Personally, I felt this topic was a little confusing to me, at least when I was reading about it. Hopefully, I made this topic a little simpler for you all. Thank you.